And my name is Mark Teehan. So I'm a principal solution architect based here in Singapore. I've been with Confluent almost 4 years. Wish everyone a happy St. Patrick's Day. Today is the Irish National Day. So it's just this talk between me and a few pints of Guinness straight after this. So I'm a principal solution engineer. So I am part of the sales team, but we're not. This is not a sales event, obviously, and so we're not going to be looking at anything regarding this products. This is an engineering focus on what Confluent have built in order to build a cloud-native Apache Kafka. I guess a little bit of background about me. I've been in Singapore for 20 years. I worked at SAP before. I mostly worked on databases prior to this, in-memory databases, and I was a DBA at Credit Suisse for a long time. So it was interesting for me to pivot over from the database world to the data streaming world, and how very, very different that is. If you're interested in anything related to Apache Kafka development, do jump on to developer.confluent.io. The one-stop shop for everything that you should know about building event streaming systems. We do have another meetup group here, the Kafka meetup group. I've spoken to that quite a lot. We used to have fairly regular cadence of meetups pre-COVID, so I'm looking forward to starting that again. And there's also a very large Slack community around some of the technology we're going to be talking about today. Not everybody knows what Kafka does. So let me just talk about that for just a couple of minutes before we get into the cloud native Apache Kafka, because if you know what Kafka is, talking about the cloud native part doesn't really help, right? So on developer.confluent.io, Kafka is a data streaming platform. It has a client server model that you're used to. Clients are things like applications, or they could be connectors. They flow into a Kafka cluster, which is a cluster of brokers. They receive the data from the clients. They store it. It's persistent. It actually has storage. So that makes it different to a messaging system. Kafka systems they're becoming more and more popular because it really bridges this sort of important gap between messaging systems and between data storage systems, such as databases and big data systems, etc. Just one or two other things that I want to point out here is whatever your preference is for clients, by and large, there's a Kafka client out there somewhere for it. With varying levels of support. Some of them are sort of skunkworks projects on GitHub. Some of them are full-blown enterprise clients. And the last thing I want to talk a little bit about, so with streaming, the reason companies are building streaming systems is to implement compositional patterns, right? Their data is coming from somewhere and we're building an event using some sort of compositional pattern, feeding it into a Kafka cluster, and then some form of pattern before before it's consumed or sent to an event sink. This is really the point of the systems that we're building. And there's a little bit of information about the actual internals, the threading model between the Kafka client and the Kafka broker in terms of how it actually, what the various queues are, how you assess whether your system is going fast or slow or whatever. Kafka is it's widely used now across all sorts of industries. I personally work mostly in financial services with banks deploying Kafka, but it's also very widely used by digital natives. We have any folks here from companies like, Grab or Agoda or Gojek. These are all organizations that are very event-centric, where a lot of the data that flows through their systems is event streaming flows rather than database flows. So that's kind of a quick tour of Kafka. So let's jump back over and see what we're going to be talking about today. So the product that Confluent has built is called Confluent Cloud. And today we're going to be looking at some of the key components of Confluent Cloud and some of the decisions around why they were built in the way that they are. We'll be talking about the Confluent Cloud control plane. It's a Kubernetes operator, how self-balancing has been implemented within Confluent Cloud, and also a little bit on infinite storage. See, Confluent Cloud is the name of the SaaS product built by Confluent, offering Kafka as a SaaS service. Okay. The first part we're going to look at is the Confluent Cloud architecture. There are two planes in Confluent Cloud, a global control plane, of which there is one global control plane for across multiple cloud providers and multiple regions. And then there are many data planes. So this architecture evolved somewhat over the last 5 years. But some of the very early decisions made were obviously to run these on Kubernetes, and also dogfooding. These data planes communicate via Kafka clusters and communicate via Kafka topics. Most of the Confluent engineering services are built using event-driven microservices deployed on Kubernetes as well. And services are very decoupled, and we're going to talk a little bit about how scaling works in just a moment. Services communicate via gRPC. I guess this sort of thing is of most interest to developers out there that are looking at serverless techniques in order to build anything like a SaaS service, where you're really abstracting away anything related to the infrastructure for whatever product you're trying to build. So the global control plane for Confluent Cloud spans the three major cloud providers, AWS, GCP, and Azure. So we have some SaaS providers, you kind of log on to AWS first and then find the SaaS. It's the other way around for us. We've built a control plane spanning all. And basically, we expand our control plane onto new regions from any of the three cloud providers when they make a new region with 3 zones available. So they tend to launch a region with a single zone, then a second zone, and then a third zone. When they reach a third zone, we will expand our control plane in order to make that zone available for the users of our product. The control plane uses Kubernetes and a database for collecting metadata. And there are various microservices that operate for front end and for authentication. I'm going to jump in. This is Confluent. I'm just going to jump in. I just want to illustrate what I mean by it spanning multiple cloud providers. When you add a cluster, the first dialogue that our users see is the cloud providers. So in Singapore, where we have multi-region available for all 3 cloud providers, all 3 of these are available. So the user can simply select where they want to build the system on AWS, on Google, or on Azure. Because the backplane spans all 3 of these, they're able to build clusters from a single organization in any cloud provider or in any region. If they have subscribed via Marketplace, then they will only see the cloud provider marketplace that they have subscribed via. Okay, that obviously makes sense. And then we have the data planes. So the control plane is a single control plane spanning all. The data planes, there are many of these. So as our customers build serverless Kafka systems, these are built within the data plane for each customer. So communication between the control plane and the various data planes is, as I said earlier, via Kafka. So these are event-driven systems. It sends control plane messages and receives status updates back from the data planes back to the control planes. Kafka is a JVM-based service, like Spark and Hadoop, etc. So it generates a lot of metrics. It uses JMX, and all of these metrics need to be shipped to various metric stores for analysis and monitoring and exposure via an API back to the customer as well. And all of this is orchestrated via our Kubernetes operator. So some of the reason that we went for this sort of architecture where we have multiple data planes with an event-driven communication back to a single control point, one of the most important one was decoupling failure points. So the data planes, of which there are hundreds or thousands, they will operate independently. So even if they're not able to connect to the control plane, they will continue to operate and provide service to the clients that are connected to each data plane. And if one data plane is problematic, it doesn't impact service to the other data planes. So that idea of decoupling is very important. Anyone that's familiar with Apache Kafka knows that this whole idea of decoupling the producers from the consumers is one of the core design principles for Kafka. And also in terms of observability and auditability. So for observability, like any SaaS product, a large portion of observing these systems is internal. The whole idea of buying a system like this is that users don't have to concern themselves with building and monitoring and staffing teams and all that sort of stuff. So we provide that monitoring on their behalf, but it means that we have a really enormous monitoring stack operating internally that's examining the metrics that are coming out of these systems. Similarly for auditability, depending on the type of customer that's subscribing to this service, there are certain standards expected, particularly when you're handling financial data or healthcare data, et cetera, to meet the audit requirements for these customers. There might be one or two people that are not on mute. By the way, if anyone wants to unmute and ask me questions, please feel free to do so. This is not a very long talk, so we have plenty of time for questions. Additional reasons why Confluent Engineering chose this model around security. It's really critical for us that the Kafka clusters within each data plane are protected. Producing and consuming has to be secure. All clients that connect to this service must use TLS 1.2, and authentication is mandatory. So this differs a bit from running Apache Kafka on premise. If you just download and install from the Apache Software Foundation, the default system doesn't use encryption, and the default system doesn't use authentication. So we switched those on in order to offer this as a SaaS service. And governance, and just having a level of schema governance. I'll show you what I mean by that. This is also another area. I'll do a cancel here, go into a cluster that's running. I just wanted to show what I mean. So lineage is actually the idea of showing streaming flows on an Apache Kafka system is fairly hard to do because of the need to sort of merge the metrics across the client and the server, and then building some form of a meaningful data flow to depict where are the various volumes of data in real time flowing through the system. So, from producers of the system on the left, right through consumers of system on the right, and then as they flow through stream processing, data flows through different topics, and it might get filtered or aggregated or joined or various other streaming operations that are occurring. This sort of stream lineage is fairly hard to build. There are a lot of tools out there that attempt to do lineage and governance on streaming systems by just acting as a client from the brokers, and it's quite hard to do. Operating this as a SaaS service means the consolidation of metrics into a single metric store makes it much more feasible to build this type of lineage depiction. And then obviously for low latency and catch up, right? The control plane doesn't have to worry about the health of the data plane because it's decoupled. It obviously does worry about the health of the data plane, but it's not a major issue if a single data plane starts to run into any issues. And these are the areas where we're dependent on the cloud provider services. These systems use quite an array of services from each of the cloud providers. When one of our customers, says, I want to build a Kafka cluster on AWS in Singapore, and I want to build a Kafka cluster on GCP in Tokyo. All of the implementation details of the various services that are needed underneath that, even underneath the Kubernetes layer for each service provider is all abstracted away. Customers don't know or care what type of machines the brokers are running on, the network connectivity between them, what is the storage type for the broker file systems and for the long-term storage, etc. And because we have all of these sorts of different dependencies on the cloud providers, that means that the possibilities of having various sort of service outages across the cloud providers is always exists. Most systems that are built are multi-zone, so the system is fully distributed across the 3 zones within a single region. And that means that there are Zookeeper nodes distributed across zones. The brokers are distributed across zones. The brokers have to be rack aware. So broker 1 needs to know that it's in zone A, broker 2 in zone B, etc. So that if there's any sort of a zone failure from the cloud provider, the brokers are spatially aware of where they are in the zones, and they're able to reconfigure. This is all part of the design. The next thing I want to talk a little bit about was the difficulty of measuring resource usage when deploying a serverless system. It was relatively straightforward if you're running any distributed system to think about, is my system busy or not busy? And as soon as it gets too busy, you just add another broker, right? Or add another HDFS node or add another Spark node or whatever. This becomes more difficult because on a SaaS service such as this, users don't even care about how many brokers are running. As long as we as a SaaS provider are meeting the obligations around data replication, the number of brokers doesn't matter. And in reality, these systems actually run a considerably higher number of brokers than you would typically find for an Apache Kafka system. So a larger number of smaller brokers rather than a smaller number of larger brokers. That tends to be a pattern. So we have this difficulty of measuring resource usage, right? How do you know when your system is approaching capacity? So we had to come up with a CKU, which is a unit of capacity for a Kafka cluster, and it really measures across 5 dimensions. So the ingress, or megabytes per second coming into the system, egress, storage, how many gigabytes or terabytes are available on the file system of each broker to store the messages that are being produced into the system. The client connections, how many clients can connect to the system? We do have some. There are some deployment patterns that have very high numbers of client connections. Sometimes it's around IoT and device level stuff. They're usually proxied before they hit the brokers. But some of the businesses, such as food delivery, et cetera, can have very high client connections into Kafka systems as well. And the number of partitions. Partitions are logically something like database tables, whatever partition for payment or vehicle or order or something like that. And there's a finite limit to how many partitions are created because each one of those uses resources on the system, open file limits and stuff like that. When you have to start and stop a system, all of these files need to be checked. So we had to come up with a way of measuring all of this. And this is something else that has occurred at least once more with Confluent Cloud, because we have another service that was somewhat difficult to express how to measure resources for the other service. It's a stream processing service. And in a similar way, we've come up with a separate unit of capacity. We find this is really good. Customers understand this. It is actually configurable. And I'm going to talk about how scaling works in the system in just a moment. So we've tried to make it like truly serverless in the sense that you just have a slider to change the size of the system. That's this control here on the right. And the user can slide it to the right and add on resources. When I flick to the next one, it has slid one notch. And so it went from 1 CKU, which offers up to 50 megabytes per second ingress, to 2 CKU, which offers 100 megabytes per second index. So it doubles. Sorry, it adds 50 megabytes per second for each notch here, and it goes all the way up to 1,200 megabytes per second. So customers like this. I mean, particularly because I work with a lot of Apache Kafka users and Confluent Enterprise and Confluent Cloud. To me, this is the best model that I've seen for expressing resource usage for a distributed streaming system. So when we expand a cluster, when a user can go in and slide this anytime in order to add more capacity, and reasons to add capacity would be things like month end, or if you're a bank, it could be payday, if you're processing a lot of sort of payroll, government or something like that. If you're a retailer, just, any of the weekends throughout the year where they have large peaks of data coming through, Black Friday type of things. So the way that this system works is when the user changes this control, it issues a request back to the control plane in order to expand resources for one of the clusters in a data plane. So the request is sent to, it's a Kubernetes capacity request, and it goes through a process, right? User request expansion, the control plane, checks, is this user request authenticated and authorized to make the change? It translated into a Kubernetes custom resource. We have been using custom resources for pretty much everything for the models deployed on our Kubernetes clusters. It will check if there is sufficient capacity to satisfy the request. Resources must be available. I'm not sure if, as far as I know, we do have some resources pre-allocated, and obviously there are finite limits to how much the cloud provider is able to provide as well. We will then execute the request on the physical stateful cluster. then persist the new state back to the mothership that which will send a message through Kafka to, and it's persisted in a database, and then notify a user on completion. So typically this takes somewhere between 30 to 60 minutes, something like that. And the user will receive a notification and an email to say that the operation is complete. So kind of refining this whole process in order to have fully automated scaling has been, a process that our engineering team has been going through for some time. It was relatively straightforward to scale upwards. It's considerably more complex to scale downwards because as we'll see in just a few slides, Kafka systems are stateful. There is data that needs to be moved around whenever we change the state of the system. So the Confluent Kubernetes operator, it basically works with Kafka, in order to ensure that Kafka cluster operations are performed. We're increasingly seeing customers deploying Kafka on, OpenShift and EKS and GKE and all these, in self-managing these systems. And I consider like halfway to serverless. By having the custom resource definitions for the various services on the cluster, the broker and the zookeeper and schema registry and whatever else they want to deploy. And then it's relatively straightforward to manage that and to scale it and etc. So we do actually offer to let customers run the Confluent operator on their own Kubernetes cluster and self-manage the system. That's not a SaaS service, but it's something that a number of customers have chosen to do. So we also, these systems, one of the things that they do that's quite difficult for distributed systems in general is rolling the cluster, right? So if we have a cluster with 32 brokers, that needs to be rolled fairly regularly for various maintenance reasons. We obviously need to upgrade and patch the system. We need to, there might be reasons to roll it from an infrastructure point of view. We may need to roll it because we're resizing the system or something of that nature. So it's taken some time to reach a point where we can let automated rolling run on the thousands of clusters as a continuous process, and it sweeps through the entire estate of clusters quite regularly and rolls everything. As with any distributed system, we need to be able to restart the nodes within the cluster without impacting service for the users. Same goes for Spark, same goes for Hadoop, right? Producers that are writing data to the system will pause briefly, usually for a couple of seconds, while they are reconnected to another broker that has been elected as the new leader for the topics that producer is trying to write to. Consumers will simply reconnect to another node and resume from the next message. So it goes without saying, but just in case anyone's wondering, when you roll a cluster, there is no loss of data, there is no duplication of data. There's a brief pause as clients reconnect to another node in the cluster, and that's how Kafka is designed. So when we're rolling brokers in the cluster, first of all, the operator will basically query cluster metrics. The first thing it needs to check is this cluster in a healthy state? And is the under-replicated partition count equal to 0? This is a really important fundamental check. Every distributed system has some form of check like this, basically saying, are all of my data replicas healthy, or is there something wrong? And it's actually not abnormal for systems to slip out of replication like this. There is, there are networks between brokers, and networks are subject to all sorts of traffic. So, you don't know when a network link between two brokers is going to be busy and experience higher latency. And that replica may lag by a few changes or then a larger number of changes, etc. And that would register as an under-replicated partition, meaning that we don't have the desired number of live replicas for this data. It's usually a very transient situation. It self-heals generally within a few seconds, but there can be situations if something remains persistently under-replicated, something may have gone wrong somewhere. So it does pre-roll validation, a whole bunch of checks to make sure that we're going to be okay to take one node out of our distributed system. So if you're running Apache Kafka, that would be restarting a VM. If you're running on Kubernetes yourself, self-managed, you're going to be restarting a pod. When we're running here as a serverless SaaS service, it is a pod sitting somewhere in Kubernetes that's going to roll as well. Rolling the broker, and as it rolls, it's reporting status back continually to the control plane. And this is the sort of area where having tons and tons of data really matters, right? So we're able to build out various patterns as we see metrics coming off a rolling broker to see whether it's progressing in the way that we expected or not. Once it's rolled, it does post-roll validation. And the final check is to make sure that it has rejoined the replicas correctly, so that it has, when you take a broker out, obviously nothing is sending data to it. So all of the data that's sitting on that broker is becoming increasingly stale because your clients are still writing to the other brokers in the cluster and they're advancing their offsets. So when this one rejoins the cluster, it has to catch up, and it's all automatic. It will basically starts consuming the data from other brokers until it reaches the current level of offset. And then if the system is configured for various brokers to be preferred brokers for specific topics, then that will happen automatically, and it'll run what's called a preferred leader election, and it reverts itself to the former state, and it doesn't keep the failed over state. Some customers prefer to keep stuff in a failed over state. We don't. We let it revert to its failed over state. So I see a couple of questions coming up here. What tools do you use for observability? Are they in-house or open source? What kind of visibility do end users have for observability? We are Datadog users, and we have sort of spoken about this publicly on Confluent. So it's needless to say there is pretty gigantic amount of data going into our Datadog SaaS service. The metrics that we use for internal observability of the system they obviously start life as standard Kafka metrics. You know, there's no change to the metrics that are generated by the Kafka brokers. How we interpret and use those metrics may be different to how, you know, various vendor products do it, or Grafana dashboards and stuff out there like that. But they're only accessible internally because that's used by our ops team to make sure that the global estate of clusters is healthy. Users can access metrics. Now, this does create a bit of a problem because JMX metrics are fed off a JMX port in the JVM. The JVMs are clearly not accessible to end users, right? Everything relating to how this is implemented is not exposed to the users. So we make the most useful metrics available via a REST API. So we ship metrics from the JVMs through a microservice, make them available at a REST API. The customer can then use any sort of a client application that's able to scrape the metrics of the REST API and feed them into a metric store. So Prometheus or InfluxDB, and then depict them on Grafana or Chronograph or whatever their tool of choice is. So metrics are available via the REST API. Kafka has about 115 metrics. There's a ton of stuff in there, increasingly obscure. So I think we have about 15 to 20 available at the moment. And these are like the heavy hitting metrics that we tend to see coming up on Grafana dashboards over and over again. Sandy asked a question, could you please share what are the best practices on Kafka consumers for the infra-specific changes shared, like rolling up or rolling down brokers? Is there an event that is sent to all consumers for such infra-specific events? No, so there's no notification sent to clients of the system that there's any sort of a state change occurring on the brokers. The reason for this is Kafka has a very thick client. When you download Kafka, you need two parts, right? You need to download the brokers and start the brokers. Then you have to download the client. It's the only way to produce and consume messages to Apache Kafka. The Kafka client is already fully compatible with state changes on the broker. So as the broker needs to do things like rolling an individual broker, which means running leader elections and moving some writer or reader clients from one broker to another one, the Kafka client knows how to do all of this, and it's all negotiated silently between the client and the server. It does mean that the applications that are running Kafka client need to run a reasonably recent client. The Apache Kafka committers and contributors are extremely careful not to break the contract between the client and the broker, and the frequency of breaking changes for the client is extremely rare. I think the last one was a couple of years ago. So technically, you can actually let your client lag by quite a few versions, and it'll still work perfectly well. It understands all of the negotiation that needs to happen with the brokers. But if you're running like a super old client, then some of this stuff may not work for you. And let me take one more question and then I continue the slides. If I run Kafka on any cloud platform, is that serverless Kafka? Also, can this be considered cloud native Kafka? So it depends on whether you're running the SaaS service that we're talking about here. So, Confluent Cloud is a SaaS service built by Confluent. This is different to installing Apache Kafka on a cloud provider. It's also different to running Kafka, either as Helm or as an operator on a Kubernetes cluster. I would call both of those cases self-managed Kafka running on a cloud platform. It's not the same as serverless. I think running on Kubernetes is halfway to serverless, but it's still not serverless, right? You still have to think about your node pool and your worker nodes. You still have to think about how much file system space you allocate. You still have to think about upgrades and rolling and management and monitoring and all that. I think a true serverless service that we have built here and our the Confluent Cloud, I think, is the only really true serverless Kafka service available. But we've had to implement all of the items that I'm talking about here. Hope that answers your question, Jin. Okay, all right, let me continue. So another important part of this, and I think converting any distributed system to a SaaS system cannot ignore the fact that it's a distributed system. It's quite different to a database monolith, right? Where everything can run on a single server. So Confluent Cloud clusters are self-balancing, particularly related to storage. So Kafka brokers tend to have large file systems. The general recommendation I have for customers is start with 1 terabyte, and you can take it all the way up to about 16 terabytes. But if you're hitting 16 terabytes, you should be adding another broker. So add a 4th broker and add a 5th broker. And then as you add brokers, you could consider having smaller file systems, because the more state you carry on each node in a distributed system, the more time it's going to take in order to do anything concerning that state. Doing any sort of an FSCK in the file system, having to scan all of that data, having to do any sort of integrity checks or anything, it just takes more time with larger file systems, obviously. And as with a distributed system, we need to think about if our system is balanced, right? And there are several dimensions to balance for Kafka, and I think this actually applies to other distributed systems as well. The number of replicas on each broker. So if we think of a topic being something like a table, and a typical Kafka system probably has 100 topics. It can have 200, 500, 1,000, 10,000, but typically we're looking at somewhere around about low hundreds, is a fairly typical. There's a bank here that runs a large central system for the whole bank with hundreds of event streaming applications connected to it, and they have 300 or 400 topics. Okay, so the replica counts, the leader counts. So every topic has a leader and followers. The amount of disk usage on each of the brokers, if we're allocating 1 terabyte, how much of that terabyte is used on each broker, and the network usage. You might be thinking here, I mean, if I have 3 brokers and I have 3 copies of the data, how do they get out of balance? And the answer is they can't get out of balance. If you have 3 and 3, then it never gets out of balance. However, as soon as you add a 4th broker to this cluster, it will start getting unbalanced, because some of the data is on some of the brokers. You do not have all of the data on all of the brokers. And that's when balance can start to tip a bit. Typical, we don't publish the size of the clusters that are running, because it's a serverless service, and we really actually don't want our customers to even think about the infrastructure that underlies this system. The whole point is we want them to focus their efforts on the client side and on processing and all that. They shouldn't be concerned with the infrastructure that it takes to run their system. Rebalancing, basically rebalancing means we're going to move data between brokers, and this becomes a big issue for us if we're running a global control plane, orchestrating over a large number of data planes, and we're automating rebalancing of systems that are just running across the entire fleet of clusters 24/7. Depending on the various triggers for doing that, then it means that we're moving very large amounts of data between the different brokers. It would not be unusual if we're rebalancing a cluster to move several terabytes of data across the network, and just the whole thing of trying to make this seamless is not easy. And I think this was one of the greatest challenges of really building a serverless Kafka system, is how to how to do these sorts of data operations in order to rebalance the cluster and keep service constant for customers without interfering with what they're doing. And the answer to this was infinite storage. So this is a fairly big project that has been a combination of effort, a large effort from the open source community and a correspondingly large effort from the internal software engineering team in Confluent. And the idea is that in reality, most streaming systems, the consumers run quickly, right? And they're able to keep up with the data writers. So if we have a producer writing in, supposing we're doing change data capture from a database, and it's writing in at 50,000 messages per second or something like that. In reality, most consumers are tuned to be able to run at more or less the speed of the producer. So whether it's a single one or a group, they'll usually be tuned to operate it that way, which means that the data actually does not reside on the brokers for very long. It actually streams through very quickly. And once the consumers consume the data, even though it's saved on the broker and it's kept there in case it's needed, actually the consumers have already consumed that. And that means that actually most of the data that we're dealing with is really the data that's in memory, and the readers are reading the data from the memory of the brokers. So this created a difficulty, right? Because if you're going to have a large number of topics and really increase the volume of storage on the brokers, then you're really increasing the state, you're increasing the actual weight of the brokers, the maintenance weight of those, when in fact the occasions where you need to go and read the old data is very, very rare because consumers are keeping up with producers, right? So the answer to this is infinite storage by having multiple tiers of storage. So the brokers have a local hot set, which is a file system that is a fraction of the size of the former file system, because we're using object storage to store most of the data. So object store on Amazon would be S3, and et cetera, for the other cloud providers, whatever object storage model that they offer. And it means that really there's really a threshold for every system between when the data lands on the system from a writer, between when all or most of the consumers have already read that data. There's an average kind of threshold there. And while your system might default to keeping 24 hours of data or 7 days of data, whatever the retention period is, in reality, most consumers probably consume the data within 10, 20, 30, 40, 50 seconds, right? When the system is operating normally. And that's the idea. So the local hot set is basically it is probably somewhat similar to the size of memory on the broker, not necessarily. It could be larger. In fact, it's most likely to be a bit larger, but not orders of magnitude larger anymore. And then most of the data is out in the object storage. And then the challenge really becomes synchronizing the hot set with the object storage. And you'll notice here, there aren't 3 object storages. So the brokers are able to consolidate back to a single replica of data again out on the object storage. So this really changes how a lot of things operate on the system, particularly rebalancing, because now when we're rebalancing, the only data that needs to rebalance is the data that's on the local hot set, because they're the only replicas. We have a single image of the data on the object storage, and this never needs to be rebalanced again. So implementing this meant that, rebalancing a large, heavy cluster with a large amount of data, sometimes we measure that in days, right? And now we measure it in like 40 minutes to rebalance a very large cluster. So this has had a really dramatic effect. Another reason is that data, so we may have an old consumer. It's perfectly normal, and it'd be fine to have a consumer that starts once a day and basically says, give me all the data, give me all the payments for the last 24 hours, because I'm a batch process and I'm not online continuously. And in that case, it's going to say, well, the last time I consumed was 24 hours ago and it was message number XYZ. It'll request message number XYZ, and that's all out on object storage by now. And the multi-tier is able to go out and retrieve all of this data from S3 or wherever it is. It's entirely transparent to the client, but it doesn't pass through the page cache, because you don't want a situation where you have relatively small serverless systems here running as brokers and you flood them with data that's coming through object storage. So it does not go through. It uses a separate network segment. I'm not sure what term we use. Sort of a separate network path, and it's independent of the activity that's happening, because these brokers are still producing and consuming, but one client has requested a large amount of data from object storage, which has to be passed through the broker back out through the application, but it does not go through the OS page cache for that broker. So it means that you can actually have both workloads running happily on the brokers. You can have batch clients that connect once a day and say, give me all the new data, and they don't have to be changed to sort of streaming clients. This has been important, I think, as people think about how to use a service like this, right? When you're doing it, when you're signing up for a SaaS service, we don't want customers to have to turn stuff upside down to use our service. We want it to be compatible with the sort of patterns that they're already using. And let's be honest, a lot of stuff is still batch, and we need to be able to support that. And this is really one of the key tools for being able to deliver that. And I'm just going to conclude with a little bit about where this is going for us. So as we summarize, the control plane, does the control, translates requests, ships everything back to the mothership. We've decoupled control planes and the data planes so that they operate independently of each other. We offer SLAs to our customers for the uptime, depending on the level of service that they've requested from us. There's an SLA associated with that. The Confluent Kubernetes operator for Kafka pretty much orchestrates and runs everything, and as a version of that has been made available for end users that want to sort of just run it on their own Kubernetes cluster. If you're comfortable, managing your own Kubernetes system, then you can just use an operator for Confluent. The real benefit is being able to use the elastic resources of the public cloud providers, while obscuring all of the implementation details of this away from our users, and scale to zero. So none of our customers are going to pay by hour for developer clusters. When developers are working 10 hours a day or 2 hours a day or whatever it is. So we do offer scale to zero. When you're not using the system, you don't pay anything for it. So we keep it provisioned. The authentication is still there. Any sort of metadata for objects you've created, like topics and partitions, etc., is still there. If you're not using it, you don't pay for it. So this idea of scale to zero is, I think, really one of the real goals of building a serverless system. You can't do scale to zero, if you're sort of just billing infrastructure back to an end user. So our vision with all of this is users really only need to think about the client application logic. Kafka, as I said, it's a big client, right? It's the client is complicated. It's able to do quite a lot, and we much rather have experts on this technology to be working with the application development teams and focus on the client side. And this sort of abstracts away all the details of how the server side runs. And, and Kafka resources magically arrive when they're needed and they disappear when they're not needed. That's the whole sort of serverless goal of what we're trying to build with Confluent Cloud. And that's it. I have to put a mandatory, obligatory, we are hiring, because we are hiring. We are headquartered for APAC in Singapore. We're at Suntech. We have quite a large team here. We're hiring all sorts of roles. So if you like the sort of stuff that I do and you'd like to be part of the same kind of team, please let us know. Jump on to the careers page if you're interested. We're a remote first company. Add me on LinkedIn if you have any questions about the sort of stuff that we do. Teehan is my surname. There's only a handful of us in Singapore. And that's it. So I hope that was good. And there's one more question regarding infinite storage. At Kafka scale, wouldn't this turn into a very costly solution in the long run? No, because it's writing to S3. Like, the whole point of object storage is that you can have vast amounts of storage at a very, very affordable cost. Turns out that Confluent, because of Confluent Cloud, has now become one of the largest users of S3 globally on the cloud providers, because so many of our customers are availing of infinite storage, and they're retaining messages in their topics forever. When I worked in the database world, there's all this maxim about never deleting data and always keeping it, because you never know what you're going to use it for in future. I think machine learning models has been the ultimate case of you don't know what you can do with your data just yet. You can always build a model in future, reconsume all of that data, and get all sorts of new insights from it. So no, it is actually quite economically viable to use infinite storage to select a retention period of infinite for your topics. It's surprisingly affordable, because I think this whole object model, the fact that we collapse from 3 replicas back down to a single replica, it does all sorts of optimization around compression and all that sort of stuff. And it's all it's all included in the SaaS cost for the service. So, you know, a user never sees a line item for S3 or how many gigabytes are out there, or transfer costs or anything related to that. It's simply infinite storage for the topic. So no, it's actually quite affordable. Thank you, John, for your question.